Okay, I like this. I'm not sure how this screen got so much bigger. I don't, well, it's not that. The camera zooms. I was teaching earlier today, and I couldn't get the screen much bigger than this. I'm wondering if it's like a resolution issue. Anyway, hey everybody, Lecture 20, Part 1. We're gonna pick up where we left off in Chapter 7, and so up to now we've looked at the capacity of wind. We did a little, we did some equations showing the power of the wind. We did that 1/2 rho AV cubed equation. We looked at a lot of different styles of wind turbines, and now we're going to sort of dig into the physics of the blades themselves. Oh, and we also kind of looked at the physics and the science of meteorology to the extent that we could. Okay. So I'm looking at figure 722. This is the next figure in the series. Types of airfoils. So A, B, and C are asymmetrical. Whoops. A, B, and C are asymmetrical, meaning that the top is a different shape than the bottom. A and C kind of look like your typical wings on an airplane. This is maybe more like what a bird's wing would look like here in B. And then this bottom one is obviously symmetric. And in this case, when we looked last time at lift and drag, we noticed that if we had a stream of air coming in from the left and going to the right, to get lift, if the angle of attack, is just, here's 0, here's, angle of attack to get some nice lift. This would be if you were trying to dive, obviously. To get some lift at a 0 angle of attack, this thing will not give it to you, this bottom one, because it's symmetric, because that same air molecule that started out at the front, that pair, they come together at the back, and the pressure is the same on the top and bottom. But if you have a symmetric blade and you want to get some lift, one way to do that is by increasing the angle of attack, and it's just given here as an alpha. All right. Now, there are two new terms offered. One is the drag coefficient. That's C sub D, and let's just look at this in general. C sub D is listed right here. So as expected, right around 0. This is a little bit seems a little bit misleading to me because, well, if the blade itself is asymmetric, this curve at the bottom will be asymmetric. I'm looking right here at 0 and thinking your minimum drag coefficient should be where the angle is 0. So where this guy is pointing straight into the wind, meaning right here, you're going to have the least amount of drag possible. So this curve, don't read too much into exactly where the belly is, but the takeaway here is that as the drag, as alpha increases, so does the drag. Until you get up to 32 degrees, you're like, oh man, this thing is really sitting out there and just pushing the wind more than giving you anything back. The next thing to look at is the lift coefficient, and so that's given on this axis between 0 and it peaks out around 1.6. And the idea here with the lift coefficient is that as wind is coming in the bottom, it's pushing the blade up. But at some point though, you get to too many degrees, let's just say 20 degrees, and whatever you were getting in lift ends up acting as a brake, and they cancel each other out. So at some angle, and again, this is just for one particular blade, you get your optimum of lift to drag, meaning that you've got as much force pushing you up as possible and the least amount pulling you back as possible. You know, and depending on what you want your velocity of your aircraft to be, you can obviously adjust this. Or, depending on what you want the performance of your wind turbine to be, you could also adjust it. So let's look at the equations really quick. This is box 7.3. And so the drag coefficient, so C sub D equals, this number at the top is drag, and this is a force equation. So drag is measured in force, or newtons. In the denominator, we've got there's a little bit of a typo. The equation has a P, but the book says rho for density. So 1/2 rho A, and this is, well, I'm writing it in the order that I'm more familiar with. So, so this is 1/2. This is rho for density. This is the area of the blade, and in this case, it's the chord times the length in square meters. So if we do that, it's the let's make sure we get this correct. So here's so A sub B equals the chord length, or the chord times the length. It's going to be in square meters, so let's call it C times L. So this is C front to back, and this is L from tip to tip. So, you know, more or less how much area is acting over that whole blade, and then V, of course, is the velocity. So this thing on the bottom, as it turns out, is also force, and we can verify that really quickly. So density is always going to be mass per length cubed. So I'm going to look at the dimensions of density. So density is mass per length cubed. Area is length squared. Velocity squared is length squared over time squared. If we simplify, we've got mass squared length cubed. Something's not quite working out correctly here. Drag coefficient. Second. Oh, no, it's fine. I was thinking of energy instead of force. So it's mass times length over time squared, and so you can think of this as F equals ma. So you know, m being mass, obviously, length per time squared as being acceleration. So that's force. It's the drag force. Let's look at the lift coefficient too. C sub L equals, and again, lift is just how much force is heading up. Drag obviously is how much is heading back and forth. And we talked about last time how these two things are always perpendicular. And it's just the same thing in the denominator. So 0.5 rho A B squared. So getting back, so you're never really going to do much about the density of air. This AB is more or less the geometry of the blade, and the velocity is just how fast the thing's going. So looking back here, what what a airfoil designer is looking for is more or less the sweet spot. And there you can do this either numerically on a computer or experimentally or both, but there's the more or less how those two numbers interact with each other. Okay, so here's an angle of attack showing that any of these streamlines, so this is, as the air comes past the foil, any of these streamlines that happen to be hitting the bottom are more or less forcing the blade up, causing it to have some lift. Also, since you're never going to really have a vacuum in there, you'll have these vortices or vortexes in the wake of the plane and the wake of the blade. That can cause some low pressure, further kind of sucking the thing up, if you will. Okay, now this is where it gets complicated. I'll just let you know, and not that easy to follow, but this is one of the most important slides in this entire chapter for understanding fundamentally how wind turbines work. So, and in this case, we're just looking at a horizontal axis wind turbine, so or a HAWT, horizontal wind axis turbine. We're looking into the front of it. That's what you'd normally see. But at the top, here's a little eyeball looking down at the blade. So that's an eyeball looking down at the blade. And this is what you would see if the thing sort of stopped moving, and that's what the blade looks like flying through the air. Okay. Now, in this case, the wind is just labeled as V naught, and V naught is blowing towards the blade. Now, the confusing part about this is that the lift that we see here, this lift arrow, is not pointing up. It's pointing out. Yeah, it's pointing. It's pointing. Well, it's pointing backwards. It's pointing behind the turbine, but it's also pointing in the direction that the blade is going. So let's see here. I'm going to try to draw this a little bit better. I'm going to try to draw it in a little bit more 3D here. So here's the blade. Here's the cell. Now, if this is the axis of rotation back here, if this is the axis, if this were a vector pointing like directly parallel to the axis of rotation, there's kind of the center line about what this thing is spinning. The force vector, I mean, it could either point this direction a little bit, or this direction a little bit, or this direction. If it's pointing this direction or this direction, it isn't going to spin. It's got to be pointing a little bit in the direction that it's actually moving. And so if we go back here, we can see that it is. It's pointing a little bit to the right. And that's what sort of drives the blade into the wind, if you will. This little guy U here is the tip velocity. Last time we did U equals omega R. So up top here is U equals omega R. So omega is how fast it's going. We talked about the fact that power is always torque times angular velocity. And V, let's take a look here. So this is V1. V1, where is alpha? Oh, okay, yeah. Let's go here. So this is V naught, and V naught equals whatever you see on the anemometer. So how fast is the wind blowing? Well, that's V naught. This other velocity that's given, so at the blade, so we still have that V naught hitting it. What the book is telling us here is that V1 equals 1 minus A V naught. So if A equaled 0, V1 or the velocity of the wind at the blade would just equal whatever the velocity was in the rest of the wind. But the fact that the blade is there is slowing the wind down. So it's going to be some number less than 1, obviously not 0. So that little alpha, that little A factor is what's slowing the blade down more or less. So you've got U pointing this direction, you've got V pointing in that direction. Again, we did a little bit of vector addition last time, but somewhere in here is this other vector called W. And that's the relative velocity. So in this case, W actually equals U plus V1. And these are all vectors. So to be more correct, what I should really be doing here is drawing. Let me just redraw. I'm going to redraw U, and I'm going to redraw V1 so that they actually add up. So in this case, to get W, which is this big guy right here, to get that, I can either well, V1 is going to change directions a little bit, but that's okay. What happened to my... I'm not getting my pen tools here for some reason. I want to... Well, I'm just going to draw right over it. Sorry. Here goes V1. right up there. There's V1, and here's U, and together U plus V1 equals W. That's the whole point. So I've added the velocity of the wind coming towards the blade, and unfortunately it doesn't look that way, plus the velocity of the tip moving through the air, and that's the relative wind velocity W, and that's what's driving the whole thing. And so it's important to note now, and now I can actually draw. And again, this is an important graph, but it's difficult to show in 3D. This arrow is the lift, and the lift is perpendicular to W. So the fact that the lift is pointing ahead of the vector around which the blade is spinning is what actually makes the thing spin. That's the whole point. Okay. Now there's one more figure showing a detail of a blade. So in general, at the base of a turbine blade is going to be thicker, than at the tip, but you can also see that as you get closer to the tip, the velocity increases. And so they've used the uppercase letter U for the actual tip velocity, and then other lowercase u's for slower, lower velocities as you get, and ultimately when you get all the way down here, the velocity is actually 0. So no big surprise there. All right, then finally, let's do one more figure, and then we'll come back and do the Betz limit. That's a good one. Okay, so the physics that we just looked at, this is actually, even though this looks more complicated, this is a little bit easier than the little bit easier. So this guy was for a horizontal axis wind turbine, and if we go here, this is for a vertical axis wind turbine, and this is figure 727. So I'll go ahead and write that down. Fig 727 is for a vertical axis wind turbine, and we covered what those were last week. Okay. Now, the thing to keep in mind on this figure is that the velocity, so the anemometer velocity, wind velocity, is coming in from the left. All of the same vectors that we talked about before are still valid. So you still have U, and this is easier because we're looking down now at the top of this blade. You still have U, which is the tip velocity, and in the case of a vertical axis, you only have one tip velocity. The whole blade is sort of traveling at the same speed. So here it comes, obviously spinning this direction, and let's just look in each case. So here's U on the top left, here's U on the top right, here's U on the bottom right, and here is U on the top right. In each case, U is the same length. It's always the same length because R hasn't changed. This vector R, the diameter of the turbine isn't changing unless you had one of those weird boat-shaped ones or something like that. The angular velocity, at a given point in time, all four of these blades are traveling at the same velocity. So the tip speed is the same length. The only thing that changes is its direction. It's always tangent to that circle. Tangent, 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 tangent. Okay. Now what does change is this V sub I, or the velocity of the wind that's hitting the blade. So in this case, it's kind of up and to the right, about the same length as the wind speed. Here it's down to the right because the blade's moving that direction now. Still down and to the right because of where the blade is, sort of moving away from it. Now that the blade is moving into it, it's sort of up and to the right. So to get the overall relative wind speed, and this thing's all over the map now, right? Because the U's were changing directions, the V's are changing directions, but this W, this relative wind speed, is what's important. Why is it important? Because the lift, which is needed to drive the thing around in a circle, has to point forward a little bit. So if we look right here, we're in good shape because this L vector is a little bit forward of perpendicular. Where my mouse is right now is perpendicular. L is ahead of that. Good thing, drives it forward. Let's look right here. Well, it's actually pointed in, but perpendicular would be where my mouse is right now. It's ahead of it. Good thing, drives it forward. Perpendicular is here. Lift is ahead of it. Good thing, drives it forward. And same deal over here. So in each case, the way this thing's designed, the lift is always driving the thing forward. Sometimes a little bit more, sometimes a little bit less. The other thing to keep in mind are the drag forces, and in each case, obviously, the drag is pulling the thing the wrong direction, pulling it the wrong direction, pulling it the wrong direction, pulling it the wrong direction. But the drag vectors are smaller than the lift vectors, and the thing spins in a circle. That's how it works. Pretty cool. So hopefully all of the meanings of these arrows are not lost. It's showing that actually is a force pushing the blade around, or in case of the drag, pulling it backwards. Okay, so those are two really important figures. I think it's time for a break, and then we'll get into the bets limit.